Hello, this is the second video of the Algorithm 3 series on further algorithms and efficiency for OCR Discrete Further Mathematics. And we will be looking at the quicksort sorting algorithm. There are PowerPoints on Integral and a number of other videos on YouTube that show a variety of sorting algorithms and may help you to visualize them in action. The formula booklet contains some of the algorithms, but your focus should be on understanding the theory and process, as you are not expected to memorize these or practice rote application of algorithms by hand. In class or practice, technology such as spreadsheets or simple programming language may be used to demonstrate the relative power of sorting algorithms for larger scale problems. However, in your assessment, you will only be asked to demonstrate your understanding of algorithms applied to small-scale problems. So, focusing in on sorting algorithms, we may want to sort a list of numbers into ascending or descending order, or a list of words or letters into alphabetical order. We might do this because we need a sorted list to perform some other algorithm, for example, the first fit decreasing algorithm. You will remember that we have already covered the bubble and shuttle sorting algorithms, and now we are going to look at this new quicksort algorithm. The algorithm works by choosing what we call pivot elements and sorting other numbers in the list to either side of this pivot, depending on whether they are smaller or larger than the pivot. The choice of pivot is a convention. Sometimes the midpoint is chosen, and sometimes the first number in the list. This will depend on the specification and sometimes on the efficiency of the chosen pivot. For example, a mid-range value, which we'll look at in further detail later on. For OCR, the quicksort will pivot on the first value, unless specified otherwise in a question. Note that questions may be set that interrogate the application of the method, for example whether the choice of pivot affects the efficiency of the quicksort algorithm. So, to sort in ascending order, these are the steps for the quicksort algorithm. Step 1. Select the pivot element, which we've already said will be this first element from the list. We then write down all of the numbers that are smaller than the pivot in a sublist to the left of the pivot, keeping the numbers in their original order. Then we write down all of the numbers that are larger than the pivot in a sublist to the right of the pivot, again keeping their numbers in the original order. Now, this is one of these occasions where you need to control your natural ability to sort the numbers for yourselves in your head and follow the algorithm carefully. Third step is to apply steps 1 and 2 to each separate sublist until each sublist contains only one number. So each iteration of steps 1 and 2 is known as a pass. In this example, we're asked to sort the following list into ascending order. So, choosing the pivot as the first number in the list, that will be the 5. We then write down all the numbers that are smaller than 5, in this case the 3 and the 1, keeping them in their original order, so still 3 and then 1, to the left-hand side of that pivot 5. And on the right-hand side, I will write the numbers that are larger, these being 8, 12, 15, 7 and 6. Note that I have not changed the order in which these appear in the original list. I have made 7 comparisons to do this. In other words, I've compared the 5 with each of the other numbers in the list. That 5 is now in the right position in terms of the ascending order. My new pivots will be the 3 as the first element of this sublist to the left of the original pivot, and 8, which is the first element of the sublist to the right. So I will compare the 3 with the 1, and the 1 is smaller, so it will move there. The 3 is then in that space fixed, and the 5 stays there. On the second sublist, so that's 1 comparison, 2, 3, 4, 5 comparisons. The 7 and the 6 are smaller than the 8, so keeping their original order, I place them there. The 8 is now in the right place for ascending order, leaving the 12 and the 15 to the right. In the next group of sublists, I note that this is a single number, so I don't have to compare that to anything. In the second sublist, the 7 is the first element, and in that third sublist, the 12 is the first element. So I'm not comparing the 1 to anything, because it's a single number. The 7 gets compared to the 6, and the 12 gets compared to the 15, so 2 comparisons. The 1 will be fixed, the 3, the 5. The 6 will be written to the left of the 7, which is now fixed, the 8. The 12 is now fixed, and the 15, being a larger number, remains on the right. I now have all the lists with only 1 number in, so because I've only got 1 number in that sublist and 1 number in that sublist, and therefore I do not need to make any further comparisons, and I can stop. You can see that I have made a total of 14 comparisons. And note that the algorithm I've applied was for ascending order. You may be asked to sort a list into descending order, and that you would need to adjust the algorithm for this. For ascending order, we put the numbers in their original order that were smaller than the pivot to the left of the pivot, and the numbers that are larger in their original order to the right. To sort a list into descending order, we put the numbers that are higher than the pivot to the left, and the numbers that are lower to the right. Our human brains would look at that list of numbers and immediately say it's already sorted, but we still need to follow the algorithm. So the first pivot would be the 9, and we would make 8 comparisons. The order will not change, but we would have fixed the 9, and the next pivot would then be the 8. We would then make 7 comparisons. No changes, no swaps, but the 8 would be fixed, and then the next pivot would be the 7, with 6 comparisons, and so on, down to the point where we would only have the 1 left that hasn't been fixed. If we total those number of comparisons, we would, using the half of n times n plus 1, find that we'd made a total of 36 comparisons. In the next video, we will look further at the order and efficiency of a quicksort algorithm.